course, in this case now we'll be looking at a case where the force of gravity is equal to the weight of object. Force of gravity is equal to what? The weight of an object. There are some cases where we have the force of gravity between two objects equal to the weight of the object. Now, force of gravity is between, of course, let's say between the Earth and another object, or between the Earth and another massive object, or between the Earth and another less massive object, right? And that object has a weight, right, as a result of its mass. The concept is, we know that the expression for gravity is what? G m, the mass of course, let's consider the mass of the object 1 and the mass of the object 2, square what? The distance of separation between them. We all know that the weight of an object is what? Mg. But you should know that gravity is between two objects. Let's consider object 1 and what? Object 2. Now, of course, and one of these objects has a mass, and resulting, let's say this is the Earth, let's say this is the object on the surface of the Earth, right? This is not how it looks like, but I'm just giving you a pictorial representation of what I'm about to do. The object has a mass of m1, right? For this case, one of those masses will cancel out, and you'll be left with what? G, the second mass, over what? R square is equal to what? Gravity due to Earth, which is acceleration due to gravity. Now we can write this thing in this case. We can write it as G is equal to G m over what? R square. We can look for the mass or distance of separation in any way. So if we're looking for the distance of separation, we're looking at what? R is equal to what? G m over what? Acceleration due to gravity. If you are looking for the mass of the object, it will become what? M is equal to G R square over what? Okay, take note, this will be square root, right? This will be square root because there's a square here, right? So if you're looking for the mass of the object, of one of those objects, we'll be having a case where this becomes G R square over what? Capital letter G, which is the gravity, universal gravitation. So any of this case, you can be asked to look for the acceleration due to gravity, and this can be due to what? Any planet, considering what? The mass of that planet. For example, you can still look for what? You can be asked to calculate the acceleration due to gravity in any planet. Of course, knowing the distance of separation between that planet and another planet, you can be asked to calculate the mass of what? The planet or that any object. So these are three ways. So that is the purpose for having what? A case where you have force of gravity equal to the weight of an object, or the weight of any object. An object can be a planet. I hope you know that. So that is the concept. Now, let us solve some sample problems involving a case where the force of attraction is equal to what? The weight of the object. This question, take down this question. Compute the mass of the Earth. Do you understand why I explain this thing? Did you get the concept when I explained that you can look for any of what? These parameters. From the concept that the force of attraction is equal to the object, to the weight of the object, and you understand why I'm saying that. Let's solve this question. Compute the mass of the Earth, assuming it is a sphere of radius 6,340 kilometers. Take G, small by G, to be 9.81, and take big G to be what? 6.6 times 10 raised to what? Negative 11. So we're having solution, and of course, let's say we should calculate the mass of the Earth, right? Taking the radius of the Earth to be what? 6,370 kilometers, which in tongues becomes what? 6370 kilo signifies 30123. So you're having meters. So of course, and they give us acceleration to gravity as 9.81, meters per second square. We are given G, of course. So with all this concept, we're going to use this formula, make use of this formula for the calculation of the mass. Of course, the mass of the Earth is equals to what? Gravity radius square over what? G. So if we substitute that, you have what? The mass of the Earth is equals to what? 9.81. Of course, the radius is 6370123. Or square over what? G. 6.67 times 10 to the power what? Negative 11. So if we substitute this value, what will be the mass of the Earth? And you should remember that we have been solving problem that we know the mass of the Earth as 5.972 times 10 to the power 24 kilogram. If you look at the previous problem, we solved that, we had that value. Now let's see if it gives us the same answer for the mass of the Earth using this formula. I hope that's understood. So let's punch this and let's see what we have. We got a value of what? 5.9679. So we're going to approximate it. This becomes what? 8 times 10 raised to the power 24 kilogram. Calculated using the principle that the force of gravity can be equal to the weight of an object. Is that understood? Now let's solve a very peculiar question. Take note. Let's solve a very peculiar question where we will see the application of this. Of course, the question says a radius of the Earth is about 6,370 kilometers. First, let's write down the parameters as we read out. Of course, they've given us the radius of the Earth is about 6,370 kilometers, and they said why that of the mass. So we have radius of the mass is given as what? 3,440 kilometers. If an object weighs 20 Newton on Earth, so we are looking at the weight of an object on Earth. So let's put the weight of an object on Earth, 200 Newton. What would it weigh on Mars? So we're looking as for the what? The weight of an object in mass. Of course, we're looking for the weight of the object in mass, right? And let's reach further. If the mass of the mass is 0.11 of that of Earth, if the mass of the what? Mass is 0.11 of the mass of the Earth. Now this is a very important relationship. Let me read out the question again. A radius of Earth is about 6,370 kilometers, and why that of the mass is what? About 3,440 kilometers. If an object weighs 200 Newton in Earth or on Earth, what will be the weight of the object on Mars? If the mass of the if the mass of mass is 0.11 of that of the Earth. Very important question. So we are going to solve this problem. But first of all, we are going to give you the force of attraction between that object and the planet Earth, and the force of attraction between that object and what? The mass. We will start solving this question. I want to give you the mathematical expression between the force of attraction of the object on Earth and the force of attraction between the object on what? Mars. So therefore we have a case where the force of attraction between the Earth and the object, let's put this as the force of attraction in Earth is equals to what? G, the Earth, the mass of the object, over what? R square. So let's put the radius of the Earth. So this is the force of attraction between the what? Earth and the object. For that of the mass, we have, so let's put force of attraction between mass. This is G mm, which is the mass of the mass of mass multiplied by the mass of the object over what? The distance of separation, which is the radius of what? Mass. So we are putting the square root radius of the mass. So these are the concepts. And we're going to equate. Now we're going to make this. Now we're going to make the mass of this object subject formula in each of these cases. So let's consider for the earth now. Making this subject formula, we have F E rho square E over what? G M E, right? When it concerns the mass of the object on earth. Now, the mass of that object on mass, in terms of mass, the mass of that object is equal to what? The force of attraction in mass, the radius of mass square, and what? G, the mass of what? Mass. So the concept is that this object's mass is equal. What makes the weight to differ is because weight is a function of the mass and gravity. And the gravity in mass and in the gravity in earth are not the same, right? We all know that gravity differs, right? The gravity, acceleration due to gravity in earth is different from the acceleration due to gravity in what? On mass. And we expect that, of course, we know that what? The acceleration due to gravity in earth is very high compared to the acceleration due to gravity on mass. So we're having a case where if this is 200 newtons, this will be lesser than 200 newtons. That's like giving you a insight of how the answer will look like. Is that understood? So of course, these mass are the same. If you weigh them in spring balance and anyhow you do it, the mass are equal. It's because of gravity we're having variations in what? The weight. So with that being so, we're going to equate the mass. Of course, the mass are equal in any of these cases, right? The mass are equal, right? That's what we said, right? Is that understood? In terms of the earth and in terms of mass, this is a two relationship, right? So let's substitute those values. If we substitute, we have what? F E rho E square over what? G M of what? The earth is equal to what? We have, for this case, we have F of mass. Of course, you should know that the gravity is equal in any case. The universal gravitation is equal in all cases, right? So the gravity will cancel out. But we have a expression that the mass of mass is equal to 0.11 of what? The mass of the earth. So we're going to write the equation and it becomes what? F E rho square over what? The mass of earth is equal to what? Fm rho m square. Anywhere you see mass of mass represent as what? 0.11 mass of earth. So after you have done this, you notice that the mass of the earth will cancel out. And when we multiply everything, which is cross multiply, we have what? F E rho square, of course, multiplied by 0.11 is equal to Fm rho m. Note, take note. Let us make the mass of the force of attraction between the mass and that object subject formula. So it's the same as dividing by what? The distance of separation of mass. Of course, the square of distance of separation of mass. This will cancel this. Fm will stand alone. Fm becomes what? Fe rho E square multiplied by 0.11 over what? Rho m square. So this can further be simplified as what? 0.11 of Fe. Of course, in brackets, we have rho E over what? Rho m, or squared. Because of these values have square. So we factor out the squares out of the two radius and it becomes this, and see what the weight and see what the force of attraction between the mass and the object is. So now if you do that, substituting all these parameters we have here, now you should note that, please note, all these things falls under the concept that, it's very important, all these things falls under the concept that the force of attraction between earth is equal to the weight of the object on earth, and the force of attraction between mass is equal to the mass of the object in mass. With all relationship we coined, so anywhere you see the force of attraction on earth representing to what? The mass of earth. You see this is the mass of earth, and anywhere you see the force of attraction, you represent it as what? The weight of the object in what? Mass. That's what we had as our expression now. Equating the force of gravity towards the weight of what? To the weight. So when we do that, it becomes what? Wm is equal to what? So let's substitute our values. This becomes 0.11 multiplied by what? 200, because this is equal to this. Is that understood? So multiplied by 200, of course, we have this. Our root is what? 6370 kilo over what? Of course, this is 3440 kilo or square. The kilo we cancel kilo, so there's no need for us to express it. That's why I did it like this. There's no need for us to express and add 10 raised to power, because normally this is 3440 times 10 raised to power 3, and this is what? 6370 times 10 raised to power 3. But for the fact that we are seeing two of them standing as the denominator and numerator, this will probably cancel this, and we'll go on to input our parameters and get the value of the weight of the object in mass. So let's punch that with our calculator. 0.11 multiplied by 200, that the weight of the object in mass is equal to 75.44 Newton. Now, our assumption is that this is a function. We said that the weight of an object in mass and earth is a function of the gravity of earth and the gravity of mass.